So if where does it come in? And then just to kind of give an idea of like from a product point of view, why this is becoming an important topic. So essentially, a lot of the benchmarks that we're currently looking at, the way they work is the language model is asked to choose a particular option, right? Essentially classify whether the answer was A, B, or C, or D. And what really happens at this point in any of these estimation or benchmarking task is that you just pick the one with the highest probability. So if it's option A or option B or option C. Now, we have learned, and this is a very well-known thing, that most of these language models, especially after fine-tuning, they are not very well calibrated. That's a technical way of saying that you can't really trust that the choice that they're giving you, they're actually confident about it, right? That if they're saying it's A, they're not telling you how confident are they that it is A, or maybe they're less confident, and in which case you would be like, maybe I will not choose this. So what uncertainty estimation techniques really do is that they, as the name suggests, they quantify that confidence. Like, yes, I am saying it's option B with 60% confidence or 90% confidence. Now, the term Bayesian there means what I just said is what a frequentist would say. But from a Bayesian point of view, rather than just giving you the confidence score, we actually give you a distribution over, hey, what does this uncertainty look like? I hope the context is clear that as we move towards creating a robust benchmarking component in InstructLab and other AI products, we'll have to start looking into how do we also go and quantify that uncertainty in the prediction. So with that, I'll hand it over to the speaker today. I don't know if you want to introduce yourself and then kick off the talk, that would be great.
Yeah, thank you, Akash. So my name is Haizhou. I'm from Rutgers. I'm working with Hao Wang, who's the PI of the ML lab of Rutgers University. So recently we've been working on this Bayesian uncertainty estimation in large language models. As Akash pointed out earlier, accurate estimation of the uncertainty is actually very crucial to a trustworthy LLM. So imagine that you have a language model and you ask the question about the most popular research direction in machine learning for the past 3 years, and it will just give you 100% uncertainty saying that it was a large language model. But if you ask the question about what will be the most valuable research topic in year 2025, well, there's still uncertainty remaining in this question. Probably it's large language models, probably there's a new computing paradigm coming out that beats the large language models. We don't know about it. So if a language model can summarize the history and give you a correct estimation of this uncertainty, it will be great. And it will help you to make a decision for yourself.
Hey, do you mind turning on your camera? I think that's some request about like
cool.
seeing you while you speak.
All right, let me see how I'm supposed to do so. All right, cool. I think this works.
That works.
Yes, cool. Thank you. All right. So this will be the outline of the content I will be talking about today. So the first section would be the background. What is the uncertainty estimation of large language models, and the two mainstream research direction for uncertainty estimation. And then I will be in detail introduce our recent work on Bayesian uncertainty estimation for large language models. And then finally, I will do a very short discussion of the future directions of this this topic. So it will include the uncertainty in generation and also the uncertainty in alignment. Oh, preface. So first of all, the most popular way that people do the uncertainty estimation in large language models is what we call the verbalized uncertainty. So the word verbalized stands for the action of directly asking the models about the uncertainty or the confidence score in the prompt. So this is a general framework that people use. So if you take a look at the prompt, you would ask the model, hey, what's the confidence of your answer? And then after go through the different prompting strategy and also the sampling strategies, so you get a bunch of the response, and then you apply an aggregator or the confidence aggregation, and they just have the average confidence of those answers, and so you have some sort of the estimation of the uncertainty. Although this topic is extremely this thread of method is extremely simple and sometimes it's very useful, but it has been very controversial. So what do I mean by controversial? So there are a lot of papers saying that this is the best way of doing the uncertainty estimation. But still, like in this paper, the authors claim that although they are useful, but they're not as good as the white box model. So if you have the direct access to the probability or distribution produced by the language models, and you use that to do some sort of the uncertainty aggregation, and then you have the quantifier and use that as the uncertainty indicator, then it will outperform the verbalized uncertainty. But of course, another branch of the researchers saying that, well, the verbalized uncertainty actually beats the so-called white box models, log probabilities at least. So this is actually a very controversial topic. But what's the most important here is that it has been lacking the theoretical supports. So by asking the model what is your confidence score, what is your uncertainty, we don't actually know the generated output from the model means. So that's the most important observation. And the other branch of the research focused on the uncertainty estimation for the downstream adaptation. And the uncertainty estimation or inaccurate uncertainty estimation happens a lot in this scenario because when you're doing the downstream adaptation, your data is usually very scarce. So if you tune the model on this very scarce data, then the overconfidence will likely to happen. So even if you have a well-calibrated pre-trained model, so here this is the confidence. If you bin the confidence score produced by the model, and then you just estimate the accuracy in each of the bin of this confidence score, and you have this calibration graph, so you can take a look at it. So even if the pre-trained model is well calibrated, and then if you do the fine tuning, it will just quickly overfit. So then this calibration error will be a apparent issue for the model.
And maybe for the general audience,
Yes.
we want to just to quickly explain when we say calibration,
Yes.
What it means and why this graph on the left-hand side is well calibrated, the other one not. So it's a very high level, very quickly. I don't want to interrupt the talk's flow, but basically, if you are well calibrated, all it means is when you say with 90%, if you're looking at the prediction logits and you're saying, hey, 90% confident this is A, you can actually trust it because on average that will match your accuracy will match your prediction. So the takeaway here is that a pre-trained model actually is calibrated. But as you were saying, as you start fine-tuning it, as you start customizing it, the expected calibration error, which is what is shown on the right-hand side, goes a little bit higher.
Yes. Thank you, Amish. So yeah, and in this case, in the uncertainty estimation for downstream adaptation, we actually have a closer setting of the traditional uncertainty estimation. So what do I mean by that? Because people have been studying the problem of uncertainty estimation for a very long time, and Bayesian neural networks is actually naturally built for this topic. So instead of having a point estimation of the outcome, we care more about the predictive distribution produced by the model. So in the branch of the Bayesian neural networks, what we do is that we instead of doing a point estimation of the parameters, we want to estimate the posterior distribution of the parameters. So we so basically, if you do this interval, then you can have the predictive distribution, and then you can use this predictive distribution to decide what is the uncertainty. So let's take regression for example. So y is a real valued label, and when you're predicting it, instead of saying that this is 1 or this is 1.5, I'm giving also if it's a Gaussian distribution, I'm also giving the variance of this prediction. So that variance could be a very useful uncertainty indicator. But the problem is that the true posterior usually in large language models or in whatever neural networks that we have today, this true posterior is usually intractable. So we don't know what is the true posterior is. So in the variational inference, what we do is that we assume that your posterior distribution to follow a very simple form. So probably it's a Gaussian. So this distribution is what we call the variational distribution. We want this distribution to approximate the true posterior distribution. So that's what we do. So basically, what we want to do is to minimize the KL divergence between your true posterior distribution and your variational distribution. So this is basically the training objective that we have in variational inference. And it turns out that minimizing this, although we don't know the true posterior here, but if you do a Bayes rule, expand this term, then you can show that minimizing this KL divergence is actually equivalent to minimizing this variational free energy, or sometimes people call it elbow evidence lower bound. So this will be the training objective that we have. So let me explain what this variational free energy represents. So there are basically two terms in this training objective. The first one, you can think of this as a data likelihood, because given W, what is the likelihood of your current observed data set? So it represents how well your model represents the data that you have collected so far. And the second term is the KL divergence. This KL divergence is actually the divergence between your approximate or variational distribution and a prior distribution that you set for your model. So in most of the cases, it's a very simple Gaussian distribution, like a standard normal distribution or a diagonal or a Gaussian distribution with diagonal covariance matrix. So this term actually represents you don't want your model to get too overcomplicated so that your model overfits to the data. So this, you can also think of this thing as a regularizer to keep the model as simple as possible. So that's the explanation of the variational free energy. But let's think about the situation of large language models. If we directly apply this kind of technique, what is the actual cost of this Bayesianization? By Bayesianization, I mean you turn the original point estimate of your parameters, and you turn it into a distribution estimation, and then of course you need to pay extra cost. But what is the extra cost? Of course, it's the large amount of extra parameters to be modeled in this case, right? So if you think of the Q of W as a Gaussian distribution, even with a diagonal covariance matrix, you need to pay double for your parameters. You have 7 billion parameter large language models. Now you need 14 billion parameters, which is not a full.
There's a question in the chat says, how can you make the weights depend on a parameter theta?
Oh yeah.
Assume, and I think the follow-up is you assume so Gaussian over the weights. Although you want to explain what that sentence means, I have no idea what you said in the second part.
Okay,
so it says here that basically there is a variational distribution Q where the weights depend on conditionally on some theta, but like the weights are basically the result of an optimization process in my normal deep learning understanding. So you have to do gradient descent over your data and you get some weights, right? But now you're assuming that those weights come from some prior, I believe, and that what I was thinking is then that prior is a Gaussian.
Yeah. So here theta, you can say also take the Gaussian as an example. So this theta could just be the summary statistics of the Gaussians. The theta is just simply the mean and the covariance matrix of a Gaussian. So if that makes sense to you, yes. All right. So okay, we have been talking about the extra cost we need to pay. But there's another branch of the techniques that we can actually utilize to bring down the computational cost for this Bayesian neural networks, which is called the parameter efficient fine-tuning techniques. So what it does, I will take LoRa as a specific example. So in low rank adaptation, what we do is that when we're doing the fine-tuning, instead of performing the full weight update on the original W0, we assume that the weight increment or the weight update to be residing in a subspace of the weights. So we say the increment can be decomposed into two low-rank matrices, so that the rank of these two low-rank matrices is significantly smaller than the original rank of the weight. So we don't need to have extra amount of parameters to be tuned in this case. So with this technique, we actually have a lot of, a couple of the preceding works that estimate the uncertainty during the fine-tuning procedure. So the first one is what we call the LoRa ensemble. You just randomly initialize a bunch of LoRa models, and then you fine-tune these models on the same data set for multiple times, with or without bootstrapping for the original data, and then you can use them as the ensemble, and because you now have multiple LoRa's, right? So you can have multiple predictions, and you see those predictions as the population sampled from a distribution of the weights, and then you use that to determine the uncertainty. Another work is what we call the Laplace LoRa. So what it does is that after the fine-tuning of the LoRa model, and then it assumes that your B and A are the mean of the Gaussian distribution, and then we estimate the Hessian of your weights on B and A, and then we say the Hessian is actually the covariance of the Gaussian distribution. And then we can have a distribution of the B and A, and then during the inference, we can sample from this distribution. So then we can also have a predictive distribution. So another work is what we call the LoRa MC dropout. So it just add another MC the dropout layer on top of the input X, and then so during the inference, your dropout is not turned off. It will still do the sampling, and you probably sample multiple times, and you also have a population from the draw from the distribution.
So this is really good, right? So I think like just as taking a step back and just like setting up where we are so far. It's like, so you started with telling us about why uncertainty quantification is a good idea, and then you showed us some traditional methods, and you really drill down on why traditional methods are costly.
Yes.
Because even in the best case approximation scenario, if you want to apply the traditional methods on a 7 billion parameter model, it will effectively be a 14 billion parameter model, because you have to at least spend one parameter per parameter to estimate the uncertainty. And then this slide is great because this is basically saying what other prior works have done in order to say, hey, instead of putting one parameter for each of the parameters in the model, I'm going to do an approximation. I'll parameterize it with low-rank adapters, LoRa, and then I'll do the uncertainty estimation on those LoRa, and hence I will reduce the number of effective parameters that I'm applying the same traditional techniques on.
Yes.
Right?
Exactly.
Great. Okay.
So now I will give a very short introduction to our first work. Is what we call the blob. It's also a Bayesian low-rank adaptation by backpropagation for large language models. It has been accepted by Neurist this year. So the main argument of this paper is we think that jointly modeling the mean and the covariance of this Q or the original distribution.
I think there's a question.
Oh, sorry.
How?
Yes. Sorry. Don't want to interrupt you. But yeah, I have a quick question regarding the setting here. So when you talk about uncertainty quantification or uncertainty estimation of large language model, like what specifically do you mean? I mean, I understand in, say, supervised learning, right? I understand, like, let's say you have an image, you want to predict the image is a dog or a cat, you know what uncertainty means, right? You know, you have, I mean, a lot of papers study that. But in large language model, especially in, generative model, when you generate a sentence or an article, typically you don't have a ground truth, right? So what specifically do you mean by uncertainty quantification here?
Yeah, that's a very good point. Actually, we're talking about the, so here now, for now, we focus on the adaptation task. Usually for the adaptation task, We have like multi-choice question answering tasks. So there is a ground truth. So it's more like the setting you mentioned before, like we're classifying an image, then we have the ground truth, and we have the confidence for each of those predictions. So yeah, for now we are focusing on this, and we're also exploring, what actually uncertainty means in the generation tasks. So we'll come back to this question later, but probably not very in depth. So yeah.
Got it. Yeah, thank you.
So the main argument that we have in this paper is that we think that jointly. So if you take a look at the previous, first of all, there are a couple of drawbacks of those preceding works. Like for LoRa ensemble, you need to train this LoRa for multiple times, which could be really costly. For Laplace LoRa, you have a MLE estimation, and then you apply the Laplace approximation to these parameters. So it might hurt the performance because it's a post-training kind of technique. And LoRa MC dropout, it just doesn't empirically work well. It's usually the weakest baseline that we have.
Always.
Yes. Yeah, exactly. So what we have is that, so what about jointly learning the mean and the variance during the fine-tuning? So what we'll do to the uncertainty estimation in this case. So the first technique that we have in this paper is what we call the asymmetric Bayesianization. So instead of thinking of B and A as the two subsets of the parameters that we want to Bayesianize at the same time, instead we only consider interpreting A as the Gaussian distributions, and we take B as the deterministic distribution. So here we assume that A are drawn from independent Gaussians, and this is just some meaningful Gaussians. The probability of A is actually equals to the product of this each individual element, and then elements B are just the deterministic. So what is good about this asymmetric Bayesianization? First of all, we can think of this, now we can project this whole Bayesianization scheme back to the full rank weight space, and we can say that we can actually see that each of the weights that we have is also a Gaussian, but they have some sort of correlation with each other. And another good thing, or advantages that we have with this asymmetric Bayesianization is that it actually reduces the sampling noise at the beginning of the training, and it actually improves the convergence. So this could be a little bit technical, but if you're familiar with LoRa, you know that when we're initializing the LoRa, we usually initialize B as a zero matrix and A as a random Gaussian matrix, right? So
Question there.
Yes.
So when you have the claim there improves coverage, how do you determine that?
Oh yeah. So
Convergence, not coverage.
convergence.
Convergence.
Oh,
Yeah,
great.
the
Sorry.
convergence speed. Yes.
Yeah, okay.
Yeah.
Sorry.
So it's just empirically we see that.
Yeah, okay.
So it's actually based on the initialization scheme that we apply to the LoRa, right? So if you have B equals to 0 and A as a random Gaussian, and you initialize the mean of the A, right? So if you also apply the noise to the B, then the B will be either positive or negative, but by expectation, you still have a zero matrix, but because during the training, you need to sample from this Gaussian distribution. And at the beginning, the B matrix will be extremely noisy, and it actually hurts the performance. So what we do with this asymmetric Bayesianization, B at the beginning, you are zero constant, so it doesn't hurt the performance. And also compared to the Bayesianizing A and B at the same time, you can actually reduce the actual additional memory cost by 50%. So that's the extra advantage that we have. So the second thing, thing that we show you is that if you apply this kind of asymmetric Bayesianization, you can actually have an interpretation of your distribution of your W in the full weight space. So here we say that the variational distribution that you apply to the full weight space is actually another Gaussian, except that this Gaussian has a low rank structure inside its covariance matrix. And this covariance matrix can be represented in this way. And here this symbol represents the Kronecker product. And one thing that we need to pay attention to here is that here the covariance matrix sigma q is strictly singular, and this Gaussian distribution is actually a degenerate Gaussian. It means that your weight distribution is actually in some lower space instead of full weight space. And it's a bit different from previous study, Gaussian distribution with low rank structure, which is still full rank, but with the structure itself is low rank. And the second thing is that because you now have a posterior distribution residing in the or degenerate Gaussian distribution as your posterior distribution, and it resides in the subspace inside the full space. So when you're designing a prior distribution for the KL divergence, you need to do some sort of design. So here we need to choose the low rank prior also on the same subspace of the posterior to guarantee that you need to set that the P of W is also a Gaussian, and also have the similar low rank structure with our transpose R equals to B transpose B. So it's just something that we show in the paper. And with this thing, we can actually, because originally, if you want to calculate the KL divergence in the full weight space, it takes a lot of time because your weight is very huge, right? You have a large natural models. Calculating those KL divergence is also unaffordable. But with this thing, with this low rank structure of the prior, then you can efficiently calculate the KL divergence inside just the only A matrix instead of the full weight matrix W. So with these two things, we actually have the final training objective. So this is the variational free energy that we mentioned before. The first term is the data likelihood, and the second term is the KL divergence that kind of constrain the complexity of your weight. So then during the inference, how do we get the uncertainty estimation? We simply estimate the expectation of your predictive distribution by sampling from your weight, right? Because now we have the variational distribution Q of W, so we can just do multiple sampling and then we aggregate the result.
But typically, how many samples do you need to get a reasonable estimate?
Yeah, that's a very good question. Empirically we see that 10 examples would be great, but also later we'll be showing that if you increase the number of the sampling, the performance keeps improving. So yeah. That's 10. I think is the most reasonable setting. All right, and there's still some other tricks that we employ to make it work because this Bayes by backprop is actually an established work probably 10 years ago. But if we naively apply this kind of technique, it doesn't work. For example. The other trick include the flip out to improve the sampling efficiency during the training. So here the flip out is, if you apply the rank 1 flip vector to your weight, so your weight can there's more diversity in your weight when you're dealing with different input inside the mini batch. So that's the advantage of the flip out. And also we need to design some KL weight scheduling because originally in the variational free energy, we have the expectation form, right? So the KL term is actually 1, but if you do the mini batch SGD, then this KL needs to be amortized to each mini batch. So usually a constant KL is not very good, so we need to do some KL weight scheduling. And also you need to do some reparameterization of the variance to improve the convergence. If you do the naive, like non-negative reparameterization here, you will not have a very good convergence speed. So we need some extra tricks here so that you can do efficient adaptation. But yeah, as you can see, it's a lot of effort to make this whole block work. But the results actually shows that the joint learning, the mean and the covariance theory, and the adaptation can improve the generalization and uncertainty estimation at the same time. So I will not go into this rows in detail, but this is the main conclusion that we have. So this is the main table from.
So maybe if you can summarize very quickly, what I'm seeing here is that across the different data sets, each one of all of these data sets are some kind of classification task.
Yes.
What we're saying is, on average, that the performance in terms of the accuracy is maintained or better than all the other methods, but you are substantially reducing the ECE.
ECE, yes, the calibration.
So your calibration is improving,
yes.
Which basically means your results are now more trustworthy, while you don't suffer any loss of accuracy.
Yes, exactly. So the next observation that we have is that training of the blob only requires slightly more computing time. So this is the standard LoRa when you're doing the fine tuning, and this is the training time. If you compare it, of course, it's a little bit slower, but it's comparable. And the memory consumption of blob is still comparable to the standard LoRa.
I have a question. Real
Yes.
quick. So when you're doing this uncertainty classification, in this uncertainty calibration or measuring, you can't do it for like classification tasks, I can imagine. But when you have like open-ended questions, like I don't know, write a poem or something like that, or even not even that, like if you wanna like answer a mathematical question, like find me a proof for this stuff. There are many ways of finding a proof, and like different things can have like, I don't know. So how do you even go about this uncertainty quantification in these more open-ended kind of tasks?
Yeah, that's a good question. So basically, I think in principle, generation task is somewhat similar to the classification task, because if you concatenate each tokens together, you just have an infinite space of the labels, but you still have a probability estimation for the generated content, right? So you still have the probability distribution for each of the tokens, and then you can just product them together. Multiply them together, and you still have the number. But the bad thing here is that actually for the generation task, the uncertainty. Well, how do I put this? The traditional uncertainty estimation technique that we develop for classification does not work that well for a generation task. That's all I know about it. I think there are a couple of recent works that we in the community that they develop a different calibration arrow for generation task based on the ranking of the tokens, but not directly on the probability distribution of the tokens. That's yeah.
All right, thank you.
Yeah, so sorry, I also have a question. I want to bring back to the table you show here, and also the table you showed in the previous slide. So you compared, here in this slide, you compared with the existing benchmark in terms of ACC and ECE. So I wonder, have you compared with them in terms of the total computational time? Because, for example, like the benchmark, or the baseline algorithm, I can imagine like if you do like ensemble learning, you want to train like a lot of models in different in parallel with different random seed. It's going to be pretty expensive. But if you do MC dropout, which is mostly inference time, like you don't need to retrain the model from scratch, should be cheaper in computation. And in the next slide, you showed the comparison with LoRa in terms of computational time. So I wonder, among the baseline and also your method, have you compared with all of them in terms of computational time?
Yeah, that's a good question. So actually, if you basically for the MLE, MAP, MCD, I would say they have almost the same computational cost and computational time. So for the training of our method, because during the training we only sample once from the variational distribution, and it's not that costly. For ensemble, it's definitely the worst one, because you need to do multiple times of training, and usually we want to avoid that. And if you measure the total compute of that, it will be multiple times of our method and also the baseline method. For LAP, it's a little bit tricky, because when you're doing for Laplace approximation here, that the training of that is almost it's exactly the same as the MLE the training.
Yeah.
But during the inference, yes. During the post-training phase, it requires the linearizing model, and it does more times of the sampling, so it's a little bit tricky to compare.
Yeah, I guess for Laplacian, like even to manipulate the Hessian matrix, it takes a lot of memory and compute.
A lot of memory and compute, exactly.
Got it. Yeah, thanks.
Thank you. So yeah, but we have actually a bad message here, because for almost all the sampling-based Bayesian method in general, blob is of course one of them. the inference time of blob is it requires significantly more compute and time. So if you compare the max memory cost and the maximum time cost of a blob, and it will be almost 10 times more than the original standard LoRa. So it remains a significant question that to be solved for the Bayesian community. How do we come up with more sampling efficient Bayesian methods to deal with this? Probably we only need to sample 3 times, and we can get a good estimation of the probability distribution instead of 10 times. But that remains for the future. And the fourth conclusion that we have is that if you scale up a little bit of the inference time compute, and you will have the improved uncertainty estimation here. So here the x-axis represents the number of the samples that you do during the inference. Then, as you can see, the ECE here in the middle, the expected calibration error keeps going down in this case, and also the NLL loss also keeps going down. The final conclusion that we have is the representation level uncertainty also aligns with the predictive uncertainty. So previously, when we were estimating the uncertainty, we focused on the prediction, right? But if you take out the internal representation of a model, because now you sample multiple weights and you have that distribution. So if you visualize it, and as you can see here, for the incorrect predictions, we have a distribution of the representation of larger variance. But for the MC dropout and also the naive Bayes backprop, it doesn't show such kind of property. But for the correct predictions, your representation's variance is smaller than the incorrect predictions. So it actually shows this kind of alignment of the representation level uncertainty and predictive uncertainty. So why do we do this kind of experiments? Because we think in the future, probably we can do some early, well, it's just some random thoughts, right? So if you have a pretty good representation level uncertainty, probably you can do some early exit before you reach to the predictive uncertainty, and you can just stop the generation of the model and just directly reject this request. So it's possible in the future. And yeah, that will be the main contribution of our recent work blob. And this is just the summarization of the experiments. But let's move forward from this work and let's think about the main challenges of the blob. And as you can see, we put up a lot of tricks or techniques to make the blob work in the case of large language models. And the main challenge, or the most important challenge of blob is that the training configuration might heavily depend on the different data distributions. And usually it's very hard for you to find the right training configuration to have a good uncertainty estimation ability. Because if your training is not right, then probably your variational distribution will collapse to a point estimation of the weights, and your prediction is not that diverse, and then there's no accurate estimation of the predictive distribution. But at the same time, if you take a look at the simple method, the verbalized uncertainty that I mentioned before, there's no good theoretical guarantees, and it's usually empirically unstable. So now the main question for us is that, can we Bayesianize a low-rank adapter? Well, we still focus on the low-rank adapter, right? In a theoretically sound and also empirically simple way. So this is the main challenge we would like to resolve in the next work. And in the next work, we propose this training-free Bayesianization for low-rank adapters of large language models. So it's built upon the blob paper, but now we don't need to figure out a correct training configuration every time for when we have a new data set. So how do we achieve that? So here, the first thing that we do is that we constrain the variational post area of the original blob paper to a low-rank isotropic Gaussians. So why do we constrain it to low-rank isotropic Gaussians? First of all, low-rank stands for efficiency. We still want to do the Bayesianization on this low-rank adapters instead of the full weights. Why do we need to make it isotropic Gaussians? Because we want this whole variational distribution family to be controlled by a single variable. And this is very important, because if you have multiple variables, then you need to do the training, the back propagation and stuff. So in training-free Bayesianization, we want to avoid that. So in practice, what we do is that so given if you have a LoRa adapter B and A, the first step we do is that we do a compact singular value decomposition of B, and then we have so now B equals to U times a diagonal matrix D times V transpose. And the next step would be getting a new pair of LoRa. Now you have B prime equals to the first two components multiplied together is U and D, and A prime is V transpose A. So you have the exact same LoRa adapter that can give you the exact same results given an arbitrary input. And now you just calculate the covariance matrix or the variance matrix of A by this. You just here the sigma q is the variable that we would like to learn for your variational distribution, and you have di is the ith singular value inside this diagonal matrix D. So we'll come back to this why we're doing this calculation, because it can exactly give you this low rank isotropic Gaussian variational distribution. So yeah. Now, as I said before, we don't have multiple parameters. So we, instead of performing the variational inference, which requires backpropagation and all those loss estimation, here we do the maximum variance search. What we do here is that, so here, this L here is, we want to keep maximizing, finding a larger variance of your variational distribution, and until the loss difference or the performance difference from between the post-Bayesianization model and the original model exceeding a certain threshold. So this basically now you don't need to do the backpropagation. You just probably have eight GPU cards, and you do this search in parallel, and you have all this performance after the Bayesianization, and you just compare what's the difference between this and the original performance, and you can decide which sigma q is the optimal one. So now this training-free Bayesianization is completed, and this algorithm is extremely simple. No backpropagation required. All you need to do is this binary search or search in parallel. It depends on the computational resource that you have at hand. So now let's talk about the theoretical guarantees of training-free Bayesianization. So the first one is our algorithm. The first, this SVD and the reorganizing the B and A and doing the inferring the variance matrix for A is that it can actually give you the low rank isotropic Gaussian posteriors. This is the first one. This is the first theorem. And the second theorem, I think, is the most important one, is that this training-free Bayesianization is actually equivalent to variational inference under certain conditions. So this is the original variational inference training objective that we have. And you can think of this as a Lagrange multiplier form of the training objective, where you have the main data likelihood you like to minimize, and data likelihood you like to maximize, and you have the complexity penalty or the KL regularizer here as a soft constraint. But here, our training-free Bayesianization with this maximal variance search, you actually have a hard constraint optimization problem. And if this L itself is an L negative log likelihood loss, and if this NL loss is locally convex within a certain threshold, and at the same time, if you set the prior standard deviation to be larger than this threshold, this equivalence holds. And it holds for a lot of natural settings. For example, you have sigma p as a standard normal distribution. This is the prior distribution, right? So the standard normal distribution is usually likely. Or you assume that the prior distribution to be uniform over the space of the weights, and then the sigma p would be infinity, and they all satisfy this this constraint. So that's all I would like to share about the training-free Bayesianization algorithm. And let's take a look at how good this thing works empirically. So in the TFB, the training free Bayesianization, improves the accuracy and uncertainty estimation across different LoRa pre-trained checkpoints. So another good thing about this TFB is that you don't need to retrain the LoRa yourself. And also a lot of, because we have Hugging Face or some other open source platforms, people just upload their LoRa adapters on different data sets. So you can just directly download those data sets and also the LoRa adapters, and you just apply the training free Bayesianization to them without training them, right? So you just need to do a search, and then you have a Bayesianized model. You can just sample from this variational distribution. And as you can see here, for different LoRa adapters, it works. There's always improvement, and sometimes it gives you the optimal ECE. That here is the calibration error. And the second thing is that TFB works perfectly with a small amount of data. So because it depends on the anchor data set D that you have for estimating the error. And if your algorithm only works for this large size of the data, then it will be really bad. But here we assume we just use a couple hundred of the data examples, and your TFB works perfectly. So that's another good thing about TFB.
So
Yes.
just to make sure I understood something here.
Yes.
So you mentioned that basically you can do this alignment directly on the LoRa layer without like loading anything into.
But you need to load LoRa here because you still need to do the inference, or you still need to do the predictions to estimate the loss.
Okay, so it's not just the LoRa layer; it's the whole model with the LoRa.
Yeah, whole model with the LoRa. But now you can do it with the torch no grab mode, right? So you don't need to calculate the backpropagation or the gradient. You only need to do the inference, the forward pass of the model. And sometimes, actually, in most of the experiments, we quantize the original model, and it works perfectly. So you can quantize it and then load the LoRa, and because the noise is added on LoRa, right? So it's not on the original model. So you can quantize the model. If the quantization is correct, everything is working. So that's another good thing. And the third observation of the TFB is that previously we say the low rank isotropic Gaussians, and we also test some other variational posterior families that can be controlled by single variable, because the essence is that we want one single variable to control this whole posterior family. And we test out the full rank noise added upon the weight, and also some constant standard deviation add on A, and the TFB, the current design is the optimal one. And the fourth one is it works on various LLM backbones. So it works on Llama 2 7B, it works on Llama 3 8B, it works on Llama 3.1 8B, even it works on the Mistral 7B. So yeah, that's a good thing about TFB. It's backbone agnostic. And it also, another good thing about TFB is that it works on different LoRa vectors. So there's a lot of variants of LoRa's, right? So you have PISA, you have Vera, or sometimes Eta LoRa. So if those LoRa adapters can be represented in B and A, because they're trained differently, but eventually they're still low rank adapters, then you can apply the TFB to those variants of the LoRa adapters, and it also works perfectly. And the last thing I would like to share is that because we say that this kind of Bayesianization method, you need to do the sampling, and sometimes it's very slow. So if you only apply the Bayesianization to your last layer, and during the inference you can cache the output of the previous layers, and then you only do the sampling on the last layer, it can actually improve the efficiency. And we show that if you use this last layer training-free Bayesianization, and you can do more sampling, do more samples during the inference, and you have less time to spend, and also you have better ECE. And so in some of the cases, if the bottleneck is the efficiency, then you can think of cutting down the budget you assign for this TFB method, and you only use the last layer TFB. And also in the experiments that we see that the hyperparameters that you search for TFB also works for that sigma Q, right? So also works for the last layer TFB. So it can be scaled very easily. So in summary, what we have discussed so far is the Bayesian large language models, LLM and TFP, they achieve better uncertainty estimation at the cost, unfortunately, of the test time efficiency. But solving that problem would be a huge research direction in the future. And the second conclusion that we have here is that we now have a very simple but effective techniques to yield the Bayesian large language models with no retraining of the LoRa adapters. You only need to do a couple of times of the forward pass, and you have the Bayesianized large language models. So these are the next steps that we have. So we have this is something that we have so far, and what are the next steps? So probably the first direction we should explore in the future is extending the Bayesian large language models to the generation tasks. And here, the figure that we show here is the some preliminary results that we have yielded recently. So using the same or similar technique of TFP, and you apply to the full weight of or the generation task without LoRa. Actually, here it's Llama 3.21b model, and here this is the y-axis represents the NLL loss that you have, and this red line represents the baseline NLL loss of your Llama model on some unseen data. If you apply the TFP here, you will have some improved NLL loss here, indicating that the uncertainty estimation or sometimes the generation quality can be improved by TFP. But we still haven't looked into the generated example here, and we're still trying to find a correct benchmark for this kind of application. And probably another direction worth exploring is having a reward model with uncertainty estimation. So we know that the test time scaling needs some reward model to kind of guide the search of your generation. And now this originally the reward model is only giving you deterministic values of those reward. But imagine that you have a uncertainty aware reward model where you actually have a range of your reward, a distribution of it. And sometimes you can be overly optimistic and choose the upper bound of this the reward that you can get, and it can kind of inspire the search algorithm that you have so far.
So this particular direction is actually something we were discussing yesterday when we heard you're coming to talk, because we're working on probabilistic sampling-based inference scaling methods.
Oh, cool.
And the reason they work is essentially because MCTS always chooses the the argmax solution.
Yes.
Which is never good for a imperfect abort function.
Mm-hmm.
And so we solve it by changing the MCTS to particle filtering.
Mm-hmm.
But then the very next thing in our list is, now that we have made sure that we're not using MCTS, how do we go and quantify the uncertainty in the abort function?
Yes.
And if you combine them together, then they kind of work really well.
Cool.
Yeah.
So yeah, if it's possible, you can apply the TFP directly.
Yeah.
It's just like
That's literally what the message I sent this morning to the group.
cool. Thank you.
So, Akash, can this be used for preference tuning?
Yeah.
Okay.
So I think in preference tuning, you still if you have a reward model and then your reward model with uncertainty, whether it's good or not, I'm not sure about it.
Because what I'm thinking is, if you have a model and then you only need to do this for.
I mean, the question is, why would you do it? Not that you can or cannot do it, but the question is, why would you do this in preference tuning?
Because if you have a model and let's say you want it to have certain behavior when you're using the same model for, let's say, chat, versus when you are using the same model for something else, more, let's say, agentic flow. So thinking more on that. Like when you are exposing to.
I think it can be applied. It's just like currently I don't have an understanding of how it will immediately benefit anything.
Instead of having to full train a model for preference, basically have the preference on the lower level.
Oh, but this work it assumes the model can generate preferences. It is not a solution for generating preferences. It's a solution of now that you can generate preference, can I quantify the uncertainty? Is that
It's only for the incentive. Okay.
Yeah, but in this case, if the reward model itself is kind of over optimized, or if so now if you
to quantify the uncertainty of a reward function, 100% you can apply. I
Yes.
think I'm just saying that like that's the method. The method is not to replace the
original,
original.
yes, yes. All right, so that will be all the things I would like to share today. Thank you guys for joining us. Yes.
This was great. Thanks everyone for joining. We still have a couple of minutes. If anybody wants to ask any questions, please unmute yourself and just fire away. I love these. Cool. I think so. I'll take the time and like maybe to say next week we'll probably going forward, like as I said, we'll announce everything on Slack. Slack channel, if you have not joined, it's called Random Samples, Red Hat Workspace. I'll try to minimize emails again. But yeah, thank you very much for joining. I'll try to send the recording. I'll see you next week.
Thank you.
Thanks all. See ya.
Adiós.